Good day, everyone. Good morning, everyone. My name is Tony. I am a course advisor and I will be your host for today's webinar. Just before we start, I'd just like to advise on some few housekeeping rules. So on your screen now, these are the notification and sound. So you are able to turn on and off the notification and sound as you wish during this webinar session. And also, please note, post any question under the Q&A function at the top right-hand corner. You will see the Q&A. So if you have any questions, you can post them there. If they are related with today's topic, our presenter for the day will be able to assist regarding that. And if it has to do with general questions, course offering, you can just post them at the Q&A box at the right-hand corner. Okay. So these are some of the common frequently asked questions. So everyone registered for this webinar will receive a copy of the PDF slide and a link to the video recording within the next 2 business days via an email. So please do check your emails, check your junk folder, spam folder, if it does not appear in your inbox. And also we will provide a free digital certificate of attendance for live attendees. There will be a QR code and a link shared after this session. So please do stay with us until the end of the session to qualify for that. Okay, can you just please guys confirm if you can hear me? I just saw someone that they cannot hear. You can just indicate on the chat box if you can hear us. Okay, so this is the event conduct. Please keep discussion lawful and respectful. Follow the moderator's direction. Do not share illegal or abusive content. Recording is not permitted unless authorized. Breach may lead to removal or referral under the ECT policies. So today's topic will be the basics of power electronics. And our presenter for the day is going to be Dr. Walid, which is also the ECT program leader. Dr. Walid, you can take control of the slide.
Okay, thank you very much, Tony. Just to check. Okay. Okay, so just to confirm, do I need now? Okay, can I control the slides as well?
Please, yes, you can take control and control the slides if you can. Can you do that?
So do you see the slides moving now?
Yes, they are moving. Yes, they are moving. Yes.
And they are full screen now.
Yes, they are, sir.
Okay.
So you can.
Thank you very much, Tony, for the introduction. And hello, everyone. In this webinar about the basics of power electronics. My name is Walid Issa, Associate Professor in Power Electronics, and will brief you today about the general information about power electronics, why it's important, and how maybe this science and this discipline is really now making a big change for a lot of countries, and it's required by a lot of also industries to bring that change to their countries as well. So the first thing that I want to talk about is what is power electronics, and maybe the topic itself is not even easy to be taught at universities. And when you go through books of power electronics, fundamental power electronics, they are sometimes difficult. And the students sometimes, or the learners sometimes have some difficulty about, okay, how to dig into this science and what's the best way to know more about this. The complexity of power electronics is not just in its format, it combines the control science, it combines the electronic science, the embedded system science, and power science, all of them together. So if you know one of them, maybe you have to know other things as well, just to, for example, to make a converter. When you look at applications around you, for example, your lights at home, your fridge, your microwave, your pumps that pumps water, for example. And if you go outside, you will find wind turbines, solar systems. All of these are integrated together. How they are integrated together? By power electronic circuit. So power electronic circuit is a term that refers to solid state electronic device used for conversion and control of electric power. We might have some very various sources, like, for example, DC sources or AC sources, and we want to convert it to a format that's good for loads, different loads. For example, batteries, machines, resistive loads, other things. And we have to make a good combination between all the signals by using a control algorithm just to make it controllable format. So power electronics is a field that combines electric power, electronics, and control. And the way that we want to just highlight today is to talk about some part of the power electronics science that's good for you to know and bring you awareness about. Maybe if you want to know more in the future, or it's good for you to know in an interview. So again, power electronics, what does it do? It provides efficient, flexible control and conversion of electrical energy. But before I just continue, I just want to make sure that if my mouse pointer is visible or no, Tony.
Yes, Dr. It is visible.
Is visible, okay, because if I'm pointing to something, I just want to make sure it's visible. Okay, so now we might have something sourced by AC. And why we have AC? Because our grid is AC, and that brings the power from the plants, for example. Maybe in the UK, we have about 220 volt or 380 if it's a three-phase. So we might have single phase or three-phase system, and we want to provide power for DC loads like heaters, lamps, DC motors. And this process now is called rectification. And how it's done? It's done by diodes or thyristors, okay? And maybe MOSFETs as well. So this is part of power electronics. We might have also DC sources like batteries, solar panels, power supplies, wind turbines, all provides DC, for example. And I want to convert it to another DC level. For example, from a battery that's a 12 volt, if I want to step it down to 5 volt to charge my phone. That is also a DC to DC conversion process here, and that can be done also by power electronics devices. I might have DC sources like batteries, like solar, and I want to provide AC. How? For example, the solar system at your houses, for example, they are solar systems and batteries together, and they are converted by some way to AC because your refrigerator, your microwave, your computer, your charger, all are AC appliances. So that's why we want to convert that to that, and that's the inversion side here. And the last link here in the loop here is the AC to AC. What things that we might need AC to AC. For example, if you have two countries and one of the countries is 50 hertz and the other country is 60 hertz, we have to have a combination between both together to convert that AC with 50 hertz to another AC with 60 hertz, and that can be done by back-to-back converter, for example, which combines the two networks by a DC bus. Another example of AC to AC, maybe at your home, is called a dimmer circuit. When you have a switch and you just turn it and you control the light intensity, maybe low intensity or high intensity, it's a dimmer circuit that converts also from AC to another AC to control the intensity and energy. So it's not going through a DC. So this is a few examples, and all of these examples should use power electronics. And yeah, based on what we see now, it's everywhere. So About the applications, we can see maybe among all the applications around us, the power electronics has been used for different purposes, but all of them do the same thing, which is converting the power level or the voltage level and current level, and provide protection, charge batteries. They are used in ventilation systems, air conditioning, refrigerator, lighting, induction heating as well. In the domestic applications, we can see them everywhere at home. And in aerospace applications, we can see them in power supplies, satellite power supplies, in telecommunication, where we have towers of telecom towers far away from grid. They can use battery, solar systems, or UPSs, and all of them use power electronics. In transportation, no doubts about it, it's all power electronics in the vehicle to charge your battery, to run your machine as well. So when we look at the market, for example, the European market, we have seen a massive investments at different levels in power electronics discipline and industry. And maybe 2 years ago, it was about $26 billion. And now in 2030, the expectation is the investments will grow to about 37, or some expectation to about $40 billion. The investments there is not just to build the converters. No, sometimes they are looking at new materials for transistors and new materials for thyristors and power diodes as well. These new materials might bring more saving in terms of power losses, and maybe in terms of size, it may be smaller. So we bring also or develop a new compact design for power electronics converters. So the investments here will happen at different levels: device type or device level, which is transistor level or diode level, silicon level, physical level, material level, or maybe at converter level, where the engineers provide the different or develop different converters to step up, step down, maybe more efficient, maybe compact, okay, or at control level as well. So all these investments have different layers. Now for the industry itself, you will see some sectors, for example, consumer sector, industrial sector, telecommunication, automotive, and material. And that's the investments in 2024 in $1 billion. And what is the expected investments in 2030, the growth of this industry? Maybe the most one that will grow to approximately double is the automotive. And there is no doubt about it, because all countries now want to shift the user from the old cars and vehicles to electrified cars or electric cars as well. So the investments in chargers, high efficiency chargers, fast chargers, and also the electric vehicle itself, new battery systems and machines as well. All that plays in the power electronics discipline. So about the market as well, we looked at, for example, jobs. What about the jobs? I just posted 2 screenshots here for jobs that I got screenshots from LinkedIn. I think 2 days ago or last week, about power electronics, and the salaries are pretty very acceptable, about 60,000 here. And when you look at the description, you will find what you need to learn. You need to learn about converters, DC converters, AC converters. You will need to learn about PWM and different control strategies like FOC, field-oriented control, or DTC, the direct torque control. You need to learn about using PCB design programs like KiCad or Altium. You need to know some machines and programs as well, like MATLAB or BSIM, and maybe one of the most popular one is Altispice. So there is another one at principal level here, which is about the salary is £75,000, which is great salary. And again, the same story for that one. So if the purpose from this slide is to know, okay, what they want, if they want to hire me, you have to learn softwares for some simulation, Blix, Altispice, MATLAB. You have to know the topology of some conversions and you have to know also the switch material properties at least. So we know that diode and transistors are all made of uh, are made of silicon, and we want to bring that efficiency to be higher. So they have replaced silicon now with something called silicon carbide or gallium nitride. So just okay. Okay, again to the story of power electronics. Why we might think about power electronics? We know the story of power generation from coal until we get it as for us in the load side. When we have, for example, coal, okay, we want to convert it to other different energy format to get it to electrical again. We might lose some stuff in the conversion. For example, 65% will be lost to get the thermal energy from coal to fuel. And in the steam turbine, to convert it to a generator, we might lose another bunch of percentage here as losses, and will bring to us later about 16.5% to consumers. So from 100%, for example, energy, condensed energy in a coal, I will get just out of it 16.5%, and the other percentage is lost. So we, until this moment, we still use the fossil fuel more than 85%. Not in the UK, in other countries as well, over all the world. And the best scenarios for this fossil fuel is to maybe last for 150 year. And what's after? What we can do? Pretty much we can't do anything now, but we have to prepare our generation next year to use the energy efficiently and even to leave for them some other energy resources. So that's why we have to develop now more efficient energy resources, and we have to use them efficiently. If we use the fossil fuel efficiently by some way, still the global warming is still a problem, because they still can be emitting some gases that make global warming, and we have still a problem. We can improve the energy conversion efficiency. We can promote more integrated renewable energy sources, okay? And that can't be done without power electronics engineer. And this is what we need to focus on. Now, if we look at a numerical example, if I have about 100 kilowatt as coal, okay, and I want to generate some energy, that energy will be 16.5 kilowatt, because the percentage of conversion here is about 16.5 kilowatt, the efficiency of the system. Now the question, the 16.5 now will go to me, to you at home. We run our appliances, microwave, power, car charger, other things at home. And what if we want to increase the efficiency of the system or the performance of the system? Do we need to invest into the consumer side or the generation side? You might think, okay, why? I want to increase the generation size because or efficiency, because I want, instead of getting 100 kilowatt, I want 120, 130. But if you look at the story from the other side, why do we spend efforts on load side? Why governments now make scientists do a lot of efforts into bringing more efficient converters, car chargers, battery chargers, more efficient laptop, for example, power supply, UPSs? That's because we need to make more savings, because the saving backward will be from 1 kilowatt to 6 kilowatt. Tony, if I may interrupt, there are a few comments that might be the screen is small or the font is small. I'm not sure how it appears from their side.
Yeah, I think Christian is just saying that the slide is not clear.
I can't hear you.
Can you hear me?
Yeah.
Yeah, and I'm just saying that Christian was just saying that the slide is not clear. So I just advise him to refresh his page. It's probably his network on his side.
On their side, okay.
Yeah, on his side. So I think everything is okay.
Okay,
You may continue, Doctor.
Yeah. Okay. So again, the question is, should we invest in the consumer side or the generation side? If you look at consumer side, if we made 1 kilowatt saving, for example, we, for example, use, instead of using battery chargers that lose 1 kilowatt, or for example, 10 kilowatt, we lost 9 kilowatts. So we have made saving 1 kilowatt, for example, that will be reflected back to the generation side as 6 kilowatt. So the investor or runner of this generator here, instead of putting 100 kilowatt coal, they might just put less by 6 kilowatt. So we have just made investments to bring 1 kilowatt efficient battery charger here, but that has been reflected back to the generation side as 6 kilowatt. Okay, and that means they need to buy the less raw material, for example, lost coal. Okay, and that might also make the service longer for the same material. So that's why the efforts about making more efficient converters and consumer side appliances is also reasonable. So it's necessary to have also higher efficiency drivers. For example, factories, they have a lot of motors, conveyors, and they have converters there to change the speed and control them. If they are done in a very efficient way, that also bring more reflected savings into the generation side as well. And that has been done by what? Or will be done by what? By who? By power excellence engineer as well. So one of the examples just I want to share with you, we have a converter, and we know we might have power input and power output, and the ratio between power input and power output is the efficiency. And the difference between power input and power output is the losses. So when you have, for example, 1 kilowatt here, you might have 0.9 kilowatt here, and 0.1 will be losses. The losses will be done by what? Or emitted by who? By power switches, by resistors, by inductors, by capacitors, and will be generated as heat. Okay, so now if we just tailor the equation a little bit, so that power input equals the power loss plus power out, and then I just compensate this power input into, or substitute this power input in this equation. I will get this version of equation and this version, and then this is the last one. So the last equation here says for me the power out from any converter equals the efficiency divided by 1 minus efficiency power loss. Okay, so there is no power input here. Okay, I just rid of the power input. So now it's a function of efficiency and power loss. And now there is a question. If I have two companies in front of me, the first company is providing converter number one. The second company is providing converter number two. And converter number one has efficiency of 85%, and converter number two has efficiency of 95%. The question now is, what about the power out? Will the power out here will be just 10% more than the power out here? We want here from this example to appreciate every few fraction of increment or enhancement in efficiency. So we have here two companies and 10% efficiency improvement here. Does it worth I take the converter number one and replace it with converter number two, or no? So if we have put both together at the same condition, so I make here power in until the power loss here reach 1 kilowatt, and I put here power in until power loss here reach 1 kilowatt as well. So they are now at the same condition. What about power out? I can use the same equation here, which is power out equals 5.7 kilowatt. So now this converter is able to give me 5.7 kilowatt. Now, what about the second converter? Will it be just 10% higher or no? To know that, we have just 10% increment in efficiency. To know that, we should apply the same equation, and the same equation gives me 19 kilowatt. So look at 19 kilowatt, look at 5.7 kilowatt. 19 kilowatt is about 3 times the first converter power out. That means if I use this converter to charge one battery, one car, I can use the second one to charge 3 cars. Okay, so now we just increase the efficiency here by 10%, but the output power at the same losses here gives me 3 times more. Okay, and that's why we fight to increase the efficiency 1% or 2% for a converter. So our goal as power electronics engineers is to bring the efficiency higher. How we do that? We have 2 routes. The first route is to look at the switches. When I say switches, I mean diodes, transistors, thyristors. Diodes, transistors, thyristors, in all decades, they are done or manufactured by silicon, but nowadays they are manufactured by different materials like silicon carbide and like GaNs. These brings more features, more properties to make a compact design and faster speed, smaller and low losses switching. And the second route is to look at topology. If I want to make step up converter or step down converter, is this a one topology there? No, we have hundreds. And you have to learn about which one is the most efficient and also the number of switches there. So there are some topologies there to bring more efficient conversion, like interleaving, switch capacitor, and also use different switching strategies like hard switching and soft switching. About the devices, when I say devices, I mean switches. When I say switches, I mean diodes, transistors, and thyristors. You have to know that the diodes in our hands is not just one type, which is just used for rectification. No, you have other types that can be used for other things. And we have the general purpose rectifier, we have high speed diodes, and we have Schottky diode. We have some limitation for these, and learning about each of them will bring your awareness about selection in another level or to another level. The transistors, we know we have BJT, but also we have MOSFETs and IGBT. And from learning about power electronics, you will know that BJT are not the one to be used in power electronics. BJT are difficult to be driven and they are losing a lot of power as heat. So they use MOSFET and IGBT. Thyristors, they are the items or switches used for dimmers, for example, or AC to AC conversion, like SCRs, GTOs, and triacs, and SET as well. For the topologies, we have here a few topologies in front of us, and each one has advantages and disadvantages. For example, the first one is step-down converter. We call it buck converter, and that has 2 switches, which is the MOSFET and the diode. The second one is also flyback converter. That is the circuit on the right-hand side that exists in your battery, laptop battery charger. Okay, and it uses here an isolation transformer because one of the requirements is to isolate the consumer laptop from the AC mains. You have to have this isolation. We can't use the buck converter for that. That's why we have to use flyback converter. But flyback converter is limited in power, maybe 100, 200 watt maximum, but not more. So we can't use this for electric vehicles. So that's why we have to use the next one, which is the bigger transformer here with 2 switches, 2 MOSFETs, and 2 diodes to make the push-pull converter, for example. The left side one here is the boost converter that can be used internally in the electric vehicle. So, for example, we have here electric car. If you look at electric car, we have battery here on the left side, and you have machine on the right-hand side. The battery is a DC, but the machine and the motor induction machine is AC. So we want to convert the DC to AC. So we're going to use something called inverter. That is the inverter here. But the inverter has a condition. They want to have here a voltage of about 800 volt. But the battery is about 400 volts. So we need to increase the voltage from battery from 400 volt to 800 volt to satisfy what? To satisfy the inverter. But here we have to insert the boost converter, which step up the voltage from 400 to 800 to make the inverter happy and then the machine as well. So that is the thing that is already in our electric vehicles. So for example, to go into the discipline of power electronics and know the things how it works, you have to know what is PWM. PWM is pulse width modulation. I think most of you might have seen that before or used that before to dim the light of a LED in using Arduino, but we have to use it now in a different way or for different application. If I have a motor and I have a battery, that battery is 9 volt and that motor is maybe 6 volt. Okay, I can connect that volt 9 to 6 volt battery and it will run, no problem. But if I want to step it down, or if I want to control the speed of the motor, what I should do? Maybe the old ages solution is to use a variable resistor. That variable resistor will change the current and drop some voltage across it, okay, to change the speed of the motor. This is the old or ancient solution. So when we look at some assumptions, some measurements, for example, if I use 1 kilowatt ohm here and maybe assume the current is 100 milliampere. And if I ask you what is the power dissipation in that resistor, the power dissipation in the resistor is called I square R. I square, which is 100 milliampere square, times R, which is 1 kilo ohm, and that will be 10 watt. Yes, I can find in the market 10 watt or 10 watt resistor, and it will be small, not very small, but it's a good one. But the power losses will be very high. Now, if I changed that resistance to not 1 kilowatt, I want to change it to 100 watt. If I change it to 100 watt and the value of the current is higher, like 1 ampere, so we have 1 ampere here square times 100, it will be 100 watt. 100 watt resistor is not small. It's not small at all. It's like your hand size. Okay, so I will use, without PWM, I will use a resistor with my hand size just to control a small motor, which is not practical at all. So that's why we can't use this stuff, because the size is very big and the losses is very high. So what is the other solution? Is to use a BJT transistor that you can put here a base in current into the base terminal, and it will control the voltage between collector and emitter. Okay, so it will work like a linear resistor. Okay, but that resistor will not change by my hand. No, it will change by a current. So if I push more current, I reduce that resistance. If I decrease that current here in the baseline, I will increase the resistance here. So let's have now just an example. This is called linear operation. If I pushed here small current, now we have something called cutoff. So there is no current here or very small current. That will bring here a transistor that will work like an open circuit. Now, if I ask you what is the voltage between the collector and emitter, the collector here is about 100 volt. The emitter here is about 0. So 100 minus 0, it will be 100 volts. So that is the point at cutoff. What if I pushed very high current into the base? That will saturate it and will turn it into a short circuit like that. Short circuit means there is no voltage between collector and emitter, and it will be 0. So that is the 0 volt here of the transistor, and that's the open circuit voltage of transistor, and that's the saturation point, and that's the cutoff point. And I can put current into the base within a range from cutoff to saturation, and that will bring me this line, which is the voltage between collector and emitter line. What about the voltage across my resistor here? If that voltage is coming out of from my transistor, for example, we have 100 volt here. If I dropped here 50 volt, the other 50 volt will be dropped at my resistor. If that drops 10 volt, that will be 90 volts. So the relation will be something like, we have here a baseline and of a transistor line, and we have here load line, look like this. So both of them will work, but in reverse action. So the voltage here, 100 volt, will be divided between the load here. The load might be a heater, might be a motor, and my transistor. So I can control the voltage across my transistor or my motor without a potentiometer, just with a variable current here, small variable current here. But we'll see that change in power dissipation later. So, for example, if I want to change my speed to be 50%, I have to put 50 volt on my machine or my heater here, and that by putting a current into the base of about IBQ according to this graph. What about the power dissipation? Now, if we look at the power dissipation, we have current here. If that transistor is taking 50 volt, my resistor also will take 50 volt. 50 volt here, and is the value of 5 ohms. So 50 volt divided 5 ohm, that means 10 ampere will go from my source into my resistor, into my transistor, into ground. So it will be 10 ampere. And if I ask you what is the power dissipated by my transistor, because I want to see if it will heat up or do I need a heatsink or no, I need to substitute by this equation, which is power of a transistor equals the voltage across my transistor, which is 50 volt, multiplied by the current in my transistor, which is 10 ampere, and that will bring 500 watt. Massive, massive power dissipation. So if you know, this approach has been used before. This approach has been used before, for example, instrument amplifiers, musical instrument amplifiers, for piano, for other things, for audio amplifiers. This approach has been used and they were really losing a lot of power. 500 watt. There is no transistor can lose that 500 watts. So what they can do, they were paralleling transistors together on a big heatsink with fan as well. So one of transistor can't do, so they use different transistors at the same time, parallel to that one, to dissipate that 500 watt. But look at the efficiency. I am just using 500 watt that's going to my motor, but losing another 500 watt as heat, not usable. So the efficiency for this circuit is 50%, and that's the point here. We can't really lose 50% every time. I'm paying for 1000 watt, but I'm losing 500 watt as heat. Okay, that's why the linear operation is not the one that we're going to use in power electronics, and we have to use PWM. PWM, we will see now the advantage of PWM. PWM, you can supply the full voltage from your battery to your motor, and that's the constant one, or you stop the supply. So that's why we can chop our supply on and off, on and off, on and off like this, and this is the PWM. The PWM, look at the average. So the motor here, because we are cutting the power supply, if we cut it very fast, the motor will not see that and see just the average point, okay, or the average value. If I cut 50 to 50, 50 offline and 50 on time, that means we have a duty cycle of 50%. So my motor will run at half speed. If I cut it 10% on and 90% off, it will run at 10% of speed. And if I run it 80% on, 20% off, that means it's running at 80% speed. Okay, so this is the pulse width modulation, and this percentage is called the duty cycle. And what's the definition of duty cycle? Duty cycle is the on time, that on time, which is 50% here, or 10% here, or 80% here, divided by the total period, which is about 100%. Okay, so now instead of using the linear operation, which lost about 500 watt, we are going to use the switch operation, which we're gonna discover now what is the power dissipation. Again, we want the goal, we want to run our machine or our motor at 50% speed. That means it should get 50 volt, not 100 volt. Previously, we just pushed here some current into the base to make the transistor drop 50, and the other 50 will be dropped by the motor. But now we will use the PWM. PWM will turn on and off my transistor into saturation and cut off only. It doesn't have any middle point. Okay, so the voltage here will be 100% or 0%. Okay, when you look at the average line, the average point that will be seen by my machine, it will be also 50 volts. So we are giving 50 volt in both cases to my machine, but we want to see how much power dissipated by my transistor. When you look at the power dissipation equation in power transistor, that's the linear, which is 500. Now, power dissipation in my transistor, if I turn the transistor on, I turn the transistor on mean I saturated. When I saturated, I means I turn the transistor to what? To a wire. Okay? That means the voltage drop here is 0. So VCE will be 0 and my current will be 20. Okay? Because 100 volt divided by 5, it will be 20. So my power dissipated, if I turned my transistor on, it will be 0 watt. What if I turn it off? If I turn it off, it will not conduct any current. So if it's not conducting any current, that means the current here is 0 and also will dissipate 0 watt. So that means here, if I turn it on, I will not dissipate anything. If I turn it off, I will not dissipate anything. So that means the average power dissipation is 0, and this is what I want. So there is a big difference between linear operation and switch operation. Linear operation, I will lose 500 watt. I need to buy 10 or 20 transistors to handle that losses, okay, and to survive. But in switch operation, I might need just one transistor because it will not lose that much. Theoretically, it will lose 0, but practically it will lose a little bit higher, but not 500 definitely. The efficiency for this one on the left-hand side is about 50%. The efficiency of the right-hand side one theoretically is 100%, but it will be maybe 95 or 90% efficient in practical application. Okay, when we look at the different power switches, we might have some passive switches like diode. When we say passive, that means we don't have ability to control it from outside. No, it controls itself by itself. So that diode is uncontrolled switch because once the voltage at the anode becomes higher than the cathode, it will turn on. What about the other transistors or thyristor switches? For example, we have BJT transistor, we have MOSFET here, and we have thyristor at the right-hand side. The transistors are fully controlled devices because I can turn them on and off by a gate or a base. I can give current or signal, it will turn off. If I release that current or signal, it will turn off. And for the thyristor, no, it's semi-controlled because I can turn it on, but I will not be able to turn it off. Okay, so there are a few devices other than this SCR that can turn off, but this one I can turn it on, but I can't turn it off. So let's look at the ideal switches. If I want to turn on and off a circuit just to make a step-up converter or step-down converter, I have to use a switch. Ideal switch, I can turn it on and it will handle any voltage, any current, okay? So the voltage across my switch, if I turn it on, it will be like a short circuit. There is no resistance for the wire. That's ideal case, okay? So the voltage across my switch terminal, it will be 0. And it can handle any value of current and in any direction. If I turn it off, yes, it will make the current exactly 0. There is no leakage current. And the voltage that can break or block, it's infinite, even in any direction. That's the ideal switch. Do we have ideal switches in our life? No. So the power dissipation for ideal switches, it will be 0 all the time. Because if I turn it on, there is no voltage. And if I turn it off, there is no current. If I multiply the voltage with current, in each case, it will be 0. But what about the practical one? So in this case, just before we go to practical, we have two types of losses. We have conduction losses, which is the middle line here, the middle point here, and it's 0. And we have the transitional or switching losses, which is 0 as well here. What about the practical switch? The practical switch, like diodes, transistors, thyristors, they can't really conduct without dropping some voltage here, okay? So the voltage will be not 0. It will drop some voltage across its terminal, maybe from the anode to cathode, drain to source, or collector to emitter. It will not be exactly 0. So if I run some current there, it will be multiplied by that voltage, maybe 0.1 volt, maybe 0.2, 0.9 volt, 0.5 volt. It will be multiplied by that volt and will dissipate some heat, okay? In turn off, it will try to block all the current and all the voltage, but unfortunately, there is some leakage current as well and have some maximum capabilities. So if I multiply the current waveform with the voltage waveform for a practical switch, I have some transition time here. That transition time between off to on or on to off, that will be for the current and voltage, that will be in multiplication to bring a power. A power has a value, it's not zero anymore. Okay, so the practical switch has a value here for power that will be transformed to heat later. Okay, so this now is also switching losses here, another switching losses here, and conduction losses. So we have two types of losses, and that losses again will be transformed as a heat, and I need heat dissipator, and I need also fan, and maybe I can't really, and maybe I need to bring more MOSFETs together to handle the current, and that will also control the compactness of the converter. Okay, so that is the power loss. As power engineers, what we need to do, we need to decrease that power loss. How? By looking at the switches. Maybe instead of using silicon, we can use silicon carbide or gallium, or we can change the topology. The topology might be loosey a lot. So that's why we have other topologies that will make a lossless conversion. Okay. So the practical switches, they do this. They really delay in transition from off to on or on to off because of the structure of the transistor. And this slides here just for references. Okay, they show the reasons why the transistor, for example, here IGBT is turning on slower than what we think because it has a capacitance inside it, and that capacitor tries to charge before it turns on the transistor. So that charging time is a delay. So that's why we have a delay here. We have a delay here for the voltage and current transition, and that will be converted like a peak here for the power. Okay. So when you look at, for example, I mentioned silicon carbide, and diodes as well. Let's just look at the diode. Okay, we know the diode. The diode is a device that blocks the current in one direction and allow it in another direction, from anode to cathode only. Okay, and that's the IV curve for the diode. But we have two types of diodes. The first diode that we maybe learned about is called signal diode, that we used in our communication circuit or Arduino circuit to protect it from reverse polarity or some simple rectification circuit. But what is the power diode? Power diode is another diode, p-n junction, but they have inserted also another layer of doped n-type material. So the signal diode is p-n junction, but the power diode is p-n junction, but the n junction is thicker because they have highly doped material and low and lightly doped material. Why they have added this kind of multi-layer n-type? Because they want to handle higher current and higher blocking voltage. They want to block thousands of voltage, not just 100 or 50 volt, and to handle high power as well. So that's why they have put more layers here. And that's the difference between signal diode and power diode. More layers, thicker, to handle higher power blockage and high current. They might call it as PIN diode. PIN means this one in the middle is silicon more than n-type because it's slightly doped. It's a pure silicon. Okay. When we look at also the speed of switching of that diode, the diode, if you, for example, bring anode here to higher voltage than the cathode, it will conduct current. But what if I make it lower? It should stop the current. Unfortunately, it will not stop the current as this line shows, the orange one here. We want this. We want to stop it as fast as possible and go to the zero line. But unfortunately, no. It will drop and conduct in reverse, so it will allow some current before it stops. Okay, allowing some current from the cathode to anode will also bring losses and will make heat for that diode, and I might replace it with a faster one. Okay, so I want to find in the market this time, by the way, is called the reverse time. Okay, reverse recovery time. So if I have a switch, if I have a diode, I want to turn it on, yes. But when I turn it off or when it turns off, I want that to be very fast. Because if it's slow, that is an opportunity for the current to go and for the voltage to build up. Voltage times current will be a power dissipation. So that's why this reverse recovery time, it will change from, for example, silicon to silicon carbide to GaN. So, and also from different types of diodes. We have in the market some diodes called rectifier diodes. We have something called fast recovery diode. That means look at this example here in the middle. The red one is the fast recovery diode, and the blue one here is the other diodes, okay? And we have something called Schottky diode. Schottky diode is also very fast one, but it can't block higher voltage. So each one has advantage and disadvantage. In power electronics, you have to be aware about all of these types, because when you select a switch, transistor or diode, you have to know which one is fast enough for your application. Maybe some application you don't need very fast one, but in fast operation you have to have the right selection. So this one is Schottky diode here that drops a less voltage. When you drop less voltage, that means your power dissipation is also low, because again, power equation is voltage times current. If you decrease the voltage or you decrease the current, in a diode, for example, in reverse direction or in forward direction, forward bias, you will have less dissipation, less losses, and less heat sink as well. So that is the differences between three popular types of diodes: the general purpose diode, fast recovery diode, and Schottky diode. Fast recovery diode, the main one is here, the third line, where we have recovery time here. So it turns off in about 25 microseconds. This is long, but if you look at fast recovery diode, it might happen in less than 5 microseconds or even less than a microsecond. In Schottky diode, it doesn't have recovery time. It switches off very quickly, which is a very good advantage. Unfortunately, it can't really handle a lot of voltage, just 100 volt. If I want battery charger 500 volt or 800 volt, I can't use Schottky. But I can use it, for example, for battery charger, laptop charger, mobile charger. Yes, I can do that. So, and I mentioned before, silicon carbide, and gallium nitride. This table is showing the properties for all of them. And the main point here is the thermal conductivity. For silicon is about 1.5. For silicon carbide is 4.9. That means when the transistor is losing power, it is able to release that power to the environment very easy. Okay, the thermal energy, it can be released to the ambient temperature, ambient atmosphere very easy. So if that number is higher, 4.9, that means it doesn't trap it inside. It releases it to outside easily. Okay, so that's the thermal conductivity point, and that means my transistor will not heat up very quickly, and it can handle the higher current as well. For other things, the band gap, that means it can handle higher and block higher voltage. I can use it not just for hundreds, I can use it for thousands of volt as well to block. Okay, so these are some materials that recently, now before 10 years, all the materials in the market are silicon. Now, from 10 years on, all the inverters in electric vehicles and solar systems are using silicon carbide. What about GaN? Yes, GaN is used now for some applications, not high voltage applications, just high, for example, mobile chargers, laptops, and data centers for AI servers as well. They use GaN because they want the things to be very small. But silicon carbide is used in big power, high power applications. So yes, you have to know about these things. For example, if you are going to interview, it's good to know about silicon carbide and GaN, the properties, the differences. You can also ask Google and ChatGPT if you want to brief yourself more about these things. So this slide is showing the application for power, silicon power. Okay, they cover all the applications for from high frequency to high power. That's at silicon. Silicon carbide now is occupying more of this application and competing with silicon. in high power and high frequency one. Okay, that's high power, high frequency. But GaN, still low power, as I mentioned, in small chargers, but high frequency. Okay, so it can handle megahertz switching. And I came now at the end of my session. I hope at least I brief you about the power electronics, give you some advantage of how to use PWM and ways of thinking about the increasing the efficiency, thinking about switching level, topology level, or other things. Thank you very much.
Thank you very much, Dr. Walid. That was very much informative, and I hope our attendees also feels the same about this webinar. As I've said before the start, I said there will be the recording will be shared to your emails. So just keep an eye on your emails after 2 business days. It should be on your email. Be on the lookout on your junk folder, spam folder if it does not appear in your inbox. And once more, thank you, Dr. Walid. So these are some of the upcoming courses, ECTs respectively. We have bachelors in industrial automation honors and electrical engineering also. And on the right-hand side, those are the dates where the program will be starting.
Have you moved your slide to the next one? Because, yeah.
Yes.
Yeah.
I did take control, right? Yes, I think I did.
Yeah.
Did. Okay. Yes. So this is the QR code. You can scan here for to access your certificate of attendance. I'm gonna share the link also on the chat where you can claim your certificate of attendance. I'm sending the link now. So I see that we didn't get any questions from the session.
No problem.
We have about 3 minutes. So let me just give the attendees 2 minutes to ask questions. If there aren't any questions at the end of the 2 minutes, we will then close today's webinar and see you on the next one.
Sure.
So on the screen, this is our contact. You can contact us on the website. We have our courses on the website also. Our head office address and also our phone numbers. So let me just leave the QR code open so that you can scan for certificate of attendance. Let's just give it 1 minute, one more minute for any questions. If there aren't any, then we'll just close. Okay, I think everything was clear from this webinar. No one seems to have any questions. And one more time, would like to thank you, Dr. Walid, for this fantastic session. It was very, very much informative. Any last words from your side, Doctor?
No, thank you very much for all your attendance and support as well.
Okay. Thank you, all the attendees, and you have a wonderful day ahead then.
Thank you.
Thank you, Dr. Walid.
Thank you. See you later. Bye-bye.
Thank you. Yes, bye-bye.